Hello everyone and welcome to Handmade Hero, the show where we code complete game live on Twitch when my microphone does not get in the way. I really need a longer cord for this thing. It actually caused us to lose a whole episode's recording, although we got it back from Twitch, just because I can't even, when I go down to adjust it, I'm in danger of bumping the power cord. But anyway, we will not let that stop us. We are in the middle of doing some rendering code here on Handmade Hero, and we found out on Friday, much to our surprise, that the optimization work that we did over the past 2 weeks to our renderer has left us with a renderer now that is actually running at 60 frames a second, 1920 by 1080, which we were not expecting. I guess machines are just extremely fast these days, and when you have a 2D game, you don't even need a GPU in the system anymore, even if you're doing full subpixel accurate rotation and all these other sorts of things, I guess. We'll see if that holds up once we start throwing more sprites and stuff at it. We'll see. It's hard to say, but we were all pretty shocked anyway, and at least I was, to find out kind of at the end of the day exactly how fast this thing was running. So, a little bit crazy. A little bit crazy, it's true, but that's where we're at. So we have some more work we need to do. What we're going to do this week is we're going to clean up all of the render code now that we kind of have things roughly working. We're going to take a snapshot kind of and look at what we have at the end of that. And then we're going to make some estimates as to, I alluded to these way back at the beginning of the optimization pass, we're going to try and make some estimates as to what we actually think our throughput should be, and how much, basically what do we think the renderer could run at capacity on this particular machine, so that we have some idea of where we're at in terms of that. It may be that we're already pretty close to the metal. It may be that we're actually far away. We really don't know. And so the goal is going to be to try and sort of catch that up, try to make some determination about that. It turns out that just by doing the straight porting work we needed to do to get things into optimizable state before we did that estimate happened to make our code extremely fast, which I guess is just how it goes sometimes. So hey, we'll take it. Anyway, we are going to be doing programming today. We may do a little bit on the blackboard, but we're going to be doing programming today. So if you want to follow along at home, today is a Day 127, so Unpack Day 126 is source code from the source archive if you have pre-ordered the game and want to follow along at home. All right, so the first order of business that we have to do here is we have to deal with something that we have not really been dealing with, and it's something that we kind of have to tidy up. And we left it till now because it wasn't really super relevant to any of the stuff we're doing, but in order to kind of finish things up, we've got to address it at this point. So if you remember where we left things, we were running quite fast actually, but we did not quite have a complete multi-threaded tiled renderer working, because if you remember, there are all of these black lines everywhere. And so everything is running quite nicely actually, but we shrunk our tiles by a little bit. Which is kind of nice because it allows us to see them, but that's certainly not what we would ever ship in the game. We don't want our game to look like it's running on a bunch of tiles. Not to mention the fact that it messes up all of our background tiles as well, because they now have the lines in them too. So there's all kinds of reasons why this is not a particularly good thing to have happening. So what we would like to do is we would like to go ahead and look at why we had to do that, and sort of get into a position where we no longer have to worry about that. Also, I have a few sort of tidbits. I double-checked these. I looked them up, and I also double-checked them with the rad folks, who, as you know, are usually the authority I would go to when I want to actually know something about how the processor works in practice, because they confront these sorts of things head-on all the time. They confirmed for me, I remember I kind of went back and forth on this a couple times, but they confirmed for me that S-fences are not necessary. Now you remember I said at the beginning, when we started talking about multi-threaded code, I said that the x64 processor had very strong memory ordering, so writes were going to be ordered in general. But then I kind of backtracked that a little bit. I was like, well, there's this S-fence instruction now. I don't know, maybe my knowledge is out of date. And I kind of said we kind of got to we kind of have to go do a little bit of reading or figure out what the truth is, so we know whether we have to insert these or not. And the answer is that it has not changed. S-fences are not necessary. And so the reason that S-fences are in there and not necessary is because of a thing, and this actually was true all the way back. It wasn't even a change from my sort of knowledge of how things worked, so that was pretty nice for me, because a lot of times on Handmade Hero, when I go to teach something, I have to kind of couch it and say, well, this is how it used to work, and then I got to go check, and oftentimes it's like it's been evolved somewhat since then, so I got to be like, all right, remember I said this? Well, that's not exactly true anymore, or stuff like this, but this is still the same since when I first learned it, so that's kind of nice. But anyway, what I want to talk about here is a thing called right combining memory, really quickly. So essentially, the way things work in the processor, hopefully it's all sort of sunk in by now, since we've talked about this many times, is that we have a CPU and it's got registers, right? And the registers are where things actually happen. So we kind of have these registers, and maybe it's a SIMD register or something like this, so it's wide and it's got a bunch of values, who knows. But point being, these registers then get written or they get read from the cache, right? And the cache is a thing that basically stores the contents of memory locations that are being frequently used by this processor. Well, anything that gets used by the processor goes into the cache first before it is used, at least most of the time. And then, it gets operated on in the cache, and then later it will get put back out to memory. So memory is out here somewhere, and it's much slower. So we're working in the cache, and then things kind of come back and forth, in and out, and so on. And this cache also happens to be a thing we talked about, cache snooping, where there's other processors and their caches, and they talk to each other to figure out who owns what memory at what times, and all this other sorts of good stuff. So the answer in terms of fencing, we talked about this, so you should all know what fencing is. On the CPU side, CPU fencing, the answer is on the x64, right? There is no need to worry about write ordering, because writes are always ordered, and so the order in which you see the writes occur in the code, meaning whatever the compiler outputs in the order, those writes will be retired in that order. Okay, so we still need that write barrier there, because the write barrier, remember, is not an instruction. It's just a thing that tells the compiler not to move stores around. But the question was, do we need to also tell the CPU not to move them around? Okay. And so the answer to why that S-fence is even there, if the CPU is always ordering instructions, is because sometimes there's actually a concept of special memory, right? In some sense, and I guess special is probably the wrong word from it. Let's just say that there are things that are memory types. Okay? So not all memory is treated the same by the processor, is basically what this means. Normally, when we have memory that we allocated and we know what's going on with it, it's something we got from the operating system as just plain old vanilla memory for our use. Those writes will be ordered. So in this case, like for example, this stuff right here, it's all just vanilla stuff. It was declared on the stack or in the heap or something like this happening. There is no need to worry about it. Those writes are strongly ordered. But there is another thing, well, I already wrote it, I'll just point to it up here, called write combining memory. And there's also other types of memory. The processor has different ways you can think about memory. So when you have a special circumstance, sometimes you get a different type of memory, and write combining memory, for example, is one of those types of memory. And what that usually is if the hardware, like say a GPU or something like this, right? In fact, I'll just write GPU here. So if a GPU or something has some memory out on the card itself, and the CPU on the sort of the main board side of things has mapped that memory, right? So basically the GPU, these two memory regions are basically like coinciding, right? So we have some GPU memory, and it's backed by some memory on the main board, and like the CPU is going to write into this memory somewhere, right? And then the GPU, like the PCI bus, is going to sort of sync these across to the GPU or stuff like this, right? So if we have some weird stuff going on here, what can happen sometimes is the memory in the machine, if it has special constraints like this, all sorts of weird things happen once the PCI bus, once the GPU is like looking at memory, or all sorts, who knows what's happening, right? When the CPU is writing to memory like this, memory that has special hardware consequences beyond the normal just storage of bits, then what happens is it has to write out cache lines in a carefully considered way, okay? Because whenever it decides to actually flush a cache line out to memory and make that considered a write, that will actually have consequences in terms of the speed at which things can be done. Because it has to make sure that the GPU can see it and that it's visible in the right way and that the GPU wasn't looking at it, so maybe it has to lock the system bus. Who knows what happens? I don't have any idea. I don't study these kinds of things at all. But the point is, complex stuff starts to be afoot here. And what that means is the CPU actually is much slower at dealing with writes that go out to this memory. So what it will often do is try to combine, right? This is where the write combining comes to. It will try to combine writes to this memory so that it does not actually have to flush them out serially, right? So the example here would be, let's say we have two cache lines, right? Here's cache line A and here's cache line B, okay? The CPU writes to this part of this cache line, and then it writes to this part of this cache line, right? Then it writes to this part of this cache line, and then it writes to this part of this cache line, right? Well, with write combining memory, it might be smarter for the CPU to wait and see what's going on here, wait for these to kind of get filled up with all those writes, and then flush them out, right? But the problem is here, if, let's say we just had the writes in order, we wrote, this was a bad idea for me to label them that way. Let me write them in the order they're written. So we have this thing gets written 1, this thing gets written 2, then this thing gets written 3, right? Well, it may end up in a situation where this thing wants to get flushed, but this thing wants to be held because it knows that the 3 is going in there and it doesn't want to write it out to memory until the 3 is in there, so it only has to do one write of this cache line out to that memory, right? Then what would happen is the 2 may end up happening before the 1. So what the S-fence is the S-fence is actually in there only for putting in memory fences when you are writing to things like write combining memory, which may reorder writes for you. If you are not writing to that kind of memory, then you do not ever have to worry about S-fence because normal memory never needs an S-fence. The writes are ordered automatically and the cache works properly no matter what you do, right? So I just thought I'd point that out. Okay, so that's that. That's write combining. That's what the S-fences are for. So we don't need that S-fence, and I've double, triple verified that. So we're all good. We only need the write barrier. That's the only part that we have to ensure is working properly. And remember, our interlock compare exchanges would be inserting memory fences anyway. So those are also fencing us, but we don't even really need to care about that too much because the write barrier is already happening for us up here. Okay. So let's talk about our other problem that we have here, which is the whole problem with us shrinking everything. So if we went down here to our tiles, you can see where we do our tile queuing. Here's our tiled render group to output thing, which goes through each of the tiles that we want to render, and it renders them, but of course it shrinks them first, and you can kind of see here that, that it's doing the shrinking, right? And so we have to ask ourselves, what is going on here? And why did we have to do this? And there's two reasons that we had to do it, and both of them we can fix by being a little bit smarter. There's one sort of nasty element to it, and you'll kind of see what we have to do to work around that, but most of it's actually just sort of a head-end problem that we can solve. So let's talk about why we were doing this shrinking. Okay, so let's talk about our tiles and our alignment here. Okay. So the first problem that we have, right, and you can kind of see that this is going to be the case, is we are always processing 4 pixels at a time, right? So at a bare minimum, when we are doing this rendering, we kind of have to know that we can always process 4 pixels at a time, right? So if, for example, our bitmap that we had allocated was not going to be a multiple of 4, so let's say that we look at how, wide this thing is. And in fact, I believe we actually had this circumstance already. If we take a look here, I think 950, because we had 1920 divided by 2, right? Oops, 1920 divided by 2. Oh, it was 960. Never mind. All right, never mind. I was going to say we might have even had that with our original thing. But never mind. So point being, we need to make sure, first of all, that if we break things up into sort of 4 pixel buckets, that there actually always will be 4 pixel buckets to do, and that we don't end up with like a 3 pixel bucket at the end and then some like either invalid or like the first pixel of the next line shows up over here, right? So the first thing we have to do is make sure we have to set up the memory so that we know we always have an even multiple of 4 pixels on for every row, right? We just flat out have to do that. That's a requirement. So there's that. But beyond that, we also have to look at the fact that we are actually currently writing our stuff unaligned, right? We do a load unaligned and we do a store unaligned for the dest, and we actually start right on or end right on the complete pixel. Remember, we had our choice of doing that. And since startup was easier for right masking, what we chose to do was end on the correct pixel. But what that means is that if we always end on the correct pixel, that means if we were actually doing something that was like this sort of, trying to think of what the right look rate, if we're always ending on a 4, right? And we were blitting something in here, then that means we're always going to kind of have a thing where the blit is actually sort of operating on sort of this wider region. Now I have to think about this. I don't know that that ever actually matters for what we're doing, though, now that I think about it. I was going to say something here about that alignment, but I don't know that we actually really care that much about that alignment. That alignment may always be fine, because either it got clipped to the boundary, or it didn't. So yeah, so we're okay there, never mind. So we don't have to worry too much about that, actually. I think that actually can stay. What we do have to worry about is, again, our tiles, right? Our tiles have to be multiples of 4 always, because if our tiles aren't multiples of 4, then even though our bitmap was multiple of 4, we would again create this situation where we have tiles that don't quite align to this 4 pixel boundary. Now you may wonder why that's actually relevant, because who cares if the tiles are or aren't? The reason for that is because we want to avoid a situation. I'm going to go ahead and mark off some things here. So here's 4 pixels, 4 pixels, 4 pixels, 4 pixels, right? Suppose that our tile boundary happened right here. So there's 2 pixels on in this tile and 2 pixels on this tile, right? So here are the pixels. So this is tile A over here, and these 2 pixels belong to tile A, and here's tile B, and these pixels belong to tile B, right? So suppose we have a situation like that. The problem that we will end up in if we allow this to happen is that our tiles are now being rendered by 2 separate threads potentially, right? Because the work queue could decide, we're not doing anything special there. The work queue could easily hand this over to core 0, right? And this over to core 1, and they could be happily going along processing these at the exact same time. Now what that means is, remember, interlocked increments and those sorts of things always work synchronous with the cores and won't have a problem. But these here are not anything like that. We load in an unaligned thing here, right? So we would potentially be loading in this part here, right, that we're trying to get at. We may be loading in some kind of a 4 wide thing. Like, let's say that this happened to be, if we we're doing it so that we ended right here, maybe we load this part right here in, right? We load this into core 0. So it's got the AABB there, right? But then core 1 may come and load that exact same thing in, right? It may also load in AABB. They both will process it, and now they'll both try to write back to it, right? And the problem is, if they both are trying to write back to this same piece of data, one of the other will overwrite the work that the other person did, right? Because this person's going to replace the AA with some new stuff, right? It's going to replace that with something else, right? Like XX or something. And it's going to try to write back XXBB here. But then this guy is going to replace the BB with something else, right? It's going to replace it with YY or something. So it's going to try to write back YY. But when it tries to write back YY, the A and the A are still in that 4 wide block. So the AA will overwrite the XX and undo the work that this core did if this core retires the memory afterwards, right? So again, strong right ordering is all fine, but you have to remember that once things get loaded into a processor, they're in the register of the processor, and that's what you're working on. The cache has no idea that that's supposed to refer to it until you go back and do a store later. So you're constantly talking about like moving this memory into the processor, working on it, and putting it back out. During that time when it is inside the processor's registers, you have no synchronization with the other cores at all. And so you'd better make sure that no two people are going to write over what each other were trying to store as data, right? So we need to make sure that we align, we absolutely have to align, I don't know what just happened there. Okay, there we go. We have to make sure that we align our tiles to these 4 wide boundaries and that nobody is ever doing any kind of unaligned fetching across those tile boundaries in any way. But I'm pretty sure there's no way they can. So even though we're doing unaligned here, I don't think that actually matters at all. We timed it, and we noticed that the aligned or unalignedness didn't seem to matter. So that was fine. We can always recheck that again later. But what we do need to make sure, so we can make that unaligned, we just have to make sure that it never crosses that boundary. We know it won't cross the boundary at the end, but in order to make sure that it also doesn't cross the boundary at the beginning, we need to make sure that these tiles are always exactly 4 wide. So let's start by doing that part, and we should be able to make sure, actually just by assertion, that the rest of it's true, because it seems like it already actually is true, and that'll be fine. So what we need to do here is say, okay, we've got our tile width, we've got our tile height that we computed. And we need to make sure that those are rounded to the nearest 4, because if we don't, then we won't be able to align those, right? Furthermore, we need to make sure that anywhere that we're writing to is actually aligned to the actual 4-byte boundary absolutely, because that's what we're actually looking at. So we kind of need to make those two things happen exactly. No, you know what? I missed one thing. We are doing our load unaligned, but all... Okay, so we do have to do the thing that I was thinking of. Sorry. Haven't paged this entire routine in. It ends wherever the bitmap ends, right? So it's going to end wherever the bitmap happened to end, which may be in the middle. But I guess that's still okay too. It really just does not matter, because as long as it's clipped to the tiles, I think we're fine. All right, never mind. I had a brain spasm and then a reverse brain spasm. Okay, so back to our plan here. What we need to do is we need to make sure that we're going to always get aligned tiles. And so what we want to do, first of all, is say, let's make sure that the output target always actually allows us to get that sort of, to get the tiling that we actually need. So what we can do is we can just count on, if we want to, we can count on the upstream code to always allocate the target to basically be correct, if that makes sense. So we have our output target, and you know what, I realize this is probably actually wrong here, because the tile width, we need to think a little bit more about what this actually means, but we can sort of talk about that in a second. What we want to do here is we want to say, all right, when we separate this into a 4x4 array of tiles, we want to make sure that we actually ended up with things that are going to be on even multiples of 4. So when we take the tile width here, we want to take a look now and see and make sure that that's what we actually got. So the tile width, right, we need to go ahead and say if, assert essentially that the tile width is, well, I should be a little more specific here. I'll tell you exactly what we need to do. So we're going to compute some tile width, right? And we could have any old resolution here. Let's say we have, the resolution that the user wanted or something was 967 pixels, right? Something like this. Well, 967 pixels, right? If I actually go and divide that by 4, so I go ahead and say, I want to do a quick calc here, 967, and I want to round it up, let's say. So I do 967 plus 3 divided by 4. I get 242.5, right? And so obviously I'm not going to fit the right number of those, that width is not actually going to be correct. I guess I could just do it this way as well, 967 divided by 4. So I know that I can fit 241 of those in there, right? I'm sorry, each one will be 241 wide, but I have to round it up in order to cover the screen, because 241.75, if I actually just tiled 241, I would be missing some pixels at the end. So 242 would have to be the width of the tiles, right? If there's going to be 4 of them, right? So there'd be 242 would be the width, right? Now 242, then we have to process these in batches of 4 pixels. That is 60.5 4 pixel units, right? So again, that's not an even multiple either, right? So really, it would have to process 61 4 pixel units in order to actually work out, right? So what we then need to go back and do is say, okay, well, if we're going to process 61 4 pixel units, right, and we know that we're going to have 4 of these, then how many does that actually give us at the end of the day? If we were going to use 4 by 61 by 4, basically, right, or 16 times 61, right? That's going to give us 976, right? So that means our effective resolution, what we're actually going to be filling here, is 976 pixels. Okay. Now, hopefully I went through that a little bit quickly, but you see what I did there? Basically, I was just saying, all right, if we were actually to do the divides and then round up, how many pixels would we have to fill at a minimum if we wanted to do always 4 pixel units and 4 chunks across a row, right? And the answer is we would have to do 976 pixels. So what we need to ensure is that the destination buffer always would allow us to overwrite the end of it by that much. Does that make sense? Because since we're going to be processing it in these batches, it just means that that's the way things are going to line up, right? And we have to be able to overwrite it by a certain amount. Now, we only really have to overwrite, we can set the clipping region, we can set that clipping line to the nearest 4 pixel boundary. So we said we wanted 967, right? And we can actually hard clip to there. So we don't need to worry about the fact that we don't really need the full 976, right? Because we can just have that final tile be kind of small, right? But that 967 will not actually work because we will actually write over that slightly. So we just have to make sure that that is rounded to a 4 pixel boundary, if that makes sense. Because what we'll do is that final tile, like each of these tiles, right, this will be 61, this will be 61, this will be 61, right, for a total of, 61 times 4 times 3, for a total of 732. So, you know, this will be 732. And then we will have 967 minus that 732, right? So 967 minus 732, and we end up with 235, right? This is 235 pixels here, right? And these guys, right, were 732 divided by 4. These guys were the, wait, I did that math wrong. What did I do wrong there? What did I do wrong there? These guys are 61 times 4. They're 244. That's what I was, yeah. So these guys are 244 each. So these guys would be 244 each for each tile, but then the final tile would be missing some, right? That's just how that would work out. And it would be 235 pixels, so that's fine. We can set the clipping region so that we only process 235 pixels, but we're going to go over by however much this is off by rounding to 4, right? So whatever 235 divided by 4 is, right, 58.75, so we would need 59 times 4, or 236, right? So it's off by 1. We just need to make sure that buffer actually supports us overwriting a little bit. We have to be able to overwrite it just that little bit, right? And then we're good. So of the things we need to do, we need to make sure that each of the tile boundaries happens on a 4 pixel boundary. We need to make sure that the final tile actually has space out past the end of it so we can overwrite that little region, because we're doing those writes, you know, that's just the way that we're doing the writes wide, potentially. And then once we have gotten all of that worked out, we should just be good to go to leave our tiles exactly, you know, fully filling the screen without any sort of borders. So that's the stuff that we need to do. And we need to ensure the alignment of the start of the row as well. We need to make sure, we've talked about alignment before, we need to make sure that that start of the row is also aligned, because if each of these is going to be aligned, we need to start it out aligned as well, right? So let's go ahead and try to put our buffer into this form as much as we can. So the first thing I want to do is I want to assert that whatever the output target's actual destination is, right? The output target, go ahead and look up what these actually are. Platform. Let's see here. Width. So the memory, right, for that, I want to make sure that that memory, if I were to look at what the memory actually is, I want to ensure that that memory is already aligned to a 4-pixel boundary, right? And now a 4-pixel boundary, remember, pixels actually take up 4 bytes of space, so we're actually talking about 16 actual bytes for 4 pixels, right? So what we want to do is make sure that if we were to look at this value ANDed with 15, so looking at those bottom bits there, we want to make sure that they are all equal to 0, so that it is aligned at the start, right? And we want to be able to assert, I'm going to turn off our optimization here. So we want to make sure that it is not, ever unaligned, right? And so right now, I guess I don't actually know if we're doing any work in the platform layer to actually make sure that it is aligned, but you can see that we are actually getting aligned, so that's a good thing. So the next thing we need to do is make sure that our tile widths, our tile heights don't matter, because our tile heights, remember, we never process 4 pixels vertically. We only process 4 pixels horizontally. So our tile widths, they happen to actually be totally fine as long as they're 4 pixels wide, right? So we can get rid of these. I guess we should leave that one. So what we want to do is go ahead and say tile width, whatever the tile width is, it needs to get rounded up to the next, to the 4-byte boundary, right? And actually we can bake that in here, I suppose, if we want to. We can just say whatever the tile width is, we can round it up by adding in first whatever the value is that we're dividing by -1. Right? That's just a little trick for getting the rounded value, because it basically, like, since we're going to truncate, we just make sure that we will put it up to just before whatever the next boundary would have been, and then divide. That way it will always give us that rounding if it happened to be over whatever the rounding point was. So this will give us the tile width rounded up to the nearest 4. Although, I guess now that I think about it, that's actually dumb. I take that back. Because we want to be able to change tile count. It just happens to be the right thing, but we want to be able to change this to any number, so let's not do it that way. Instead, let's go ahead and say we just want to round this guy. So we want to take tile width, right? And we want to, whatever the result value is of tile width, we want to round it to the nearest 4. So what I'm going to do there is I'm going to do tile width, I want it to add in 3 and divide by 4, right? So I want to do what I was doing there, but I want to do it after the fact, so that we actually ensure that we've done that rounding. So that will give us the actual number. If I then multiply it by 4 at the end, that will give us the actual number rounded up, right? So if we take a look in here, I want to see what numbers we were actually getting. It may be that we're already getting those numbers anyway. Like I said, we kind of just put that in there because we wanted to be safe about it, but we may have already actually been getting numbers that didn't actually need to be rounded. So let's go ahead in here. So if we take a look at tile width, right? Oops, I want to do that before. So we take a look at tile width. It's already 64, which is already plenty divisible. So that's not going to be a problem. Let's go ahead and let it run. So that those are probably ground chunks that are coming in here. So let's go ahead and do this again. 480. Run it. 480. So we're actually already getting ones that are nicely rounded. We may have to test them with some sizes that aren't rounded just to make sure that our math is working here properly. But what are you going to do? So this will do the truncation, and then it will multiply back out. So this will leave us with a value that's properly rounded. So then what we need to do is we need to make sure that that final tile width actually accounts for the fact that it's going to be smaller, right? So what we need to do is we need to do a final tile width, and that final tile width needs to be whatever the total was, so whatever the full screen size is, minus the tiles that will actually be this sort of potentially inflated size, right? So we need to say whatever the tiles that would have been done besides the final tile, that final tile only accounts for however much is left, right? Then what we need to do in here, when we're doing this, right? Well, actually, now I think about it, we could actually do this a little bit easier. In fact, you know what? We don't even need to do that. All we need to do is when we do our clip rec max, our maximum there, all we need to do is say, you know what? If that clip rec maximum would actually be greater than the actual output target, then just go ahead and set it to the output target, right? That'll automatically clip us when we get to the end. So that's as easy as doing anything else would be, right? So then if we go in here, we no longer need to do these sort of adjustments because we're trying to sort of take care of that in a separate way. So now we've got our tile width adjusted, and we can sort of say, let's go ahead and make sure that you know, that all works. Let's run that here, see how we're doing. Uh-oh. We are loading from something that is not allowed. Hold on a second. The clip rep max out is greater than the output target width equals output target width. That looks correct to me. All right, so we'll have to go debug this and see what's going on there. Of course, I don't actually know if we actually did render enough. Oh, you know what else I can do? I'll go ahead and make it so that we're also running single-threaded for the moment so that we can not have to worry about multiple threads while we're debugging, which is kind of nice. By the way, in the thread view, I don't know if you guys noticed, you can see our worker threads, right? And they're all chilling in thread proc, waiting for work. They won't do anything since now we're not pushing them on. We're single-threaded right now, but just so you can see them all in the thread window, there they are. We made those. All right, anyway, so we're loading off of nonsense here, unfortunately, and I'm not sure where we actually are. So xi equals what? Min x equals -1. So this backed up behind the pixel boundary. Okay. So right, we're only clipping to the end, but we don't handle any clipping at the beginning. All right, so this may actually be the thing that I keep saying that we need to think about, and then when I go in and look at it, we don't need to think about it. But let's see if this is actually it. I think that would actually be it. So here you go. So the way that things are working at the moment, yeah, okay. So this is what this is the problem. I sort of went in and said, oh, it won't happen on this end, but it will happen on the other end. So we will have to deal with it. I knew we'd have to deal with it at some point. So the problem that we have right now is when you blit something in, right? And I guess I'll do it over here first. So when you blit something in, here's a screen and here's this is the bitmap. We align things to the end of the blit. So this will get clipped, right? The rectangle will get clipped. And then we'll start at this end in terms of lining things up. And we'll kind of go like this, right? Where each of these is 4 pixels. And, you know, this part doesn't matter because it gets masked. It won't get written. And we'll fill them in here, right? But the problem is if we do that over here on this side, right? Yes, we will do the clipping. But then when we actually do the 4 pixel alignment bit, right? We will end up being off sort of on the end, right? And we'll be writing into the beginning of the buffer here. Which obviously is not, you know, is not particularly useful. That's not particularly, that's not great, right? It's not fabulous. So I feel like the easiest way to solve that problem, and this is what I was saying before, but then I was like, maybe we don't need to do it at the end. It's true, we don't need to do it at the end, we need to do it at the beginning, because of the way we wrote the routine. I feel like the way to solve this problem properly is we would need to make sure that we always allocated some extra space at the beginning. However, which would be trivial for us to go and do. However, this presents a problem for us, it presents a problem that is the problem that I kept alluding to, and that I, was saying we maybe wouldn't have to face, because I was like looking through it and going, no, but we do have to face it. And that is what happens when this occurs at a tile boundary, right? So I was saying up here that this would be a bad condition. Well, guess what? That is exactly what will happen if we have a bitmap that happens to end, say, right here, but that is 6 long, right? Because we'll align it so that we're writing to these 4 pixels, but then when we go to write these, we'll actually be talking about this set of 4, even though there are only 2 we're going to write, and we'll end up with that problem with the writing, right? So what that says to me is we do actually have to do the thing that I kept thinking we would have to do, which is that we will have to make sure that we are essentially always writing aligned, and that we mask both our front and our back, right? Because remember, the reason that we were writing unaligned is so that we could avoid having to do one of the mask writes. What can I say? That's just the way it is. Sometimes you try to avoid it and it doesn't work. So that's what we're going to have to do. And the reason that it's a little bit annoying, I'll show you why, is because before, there's no magic to it. It's exactly what we did here, right? What we did is we said, okay, when we're starting up, we know how much we're going to fill, and if the fill width is not actually going to be aligned, then we need to align the start, right? And so that's all we really did, was just align that start, right? I'm sorry. We need to make a mask for the start, and then go ahead, right? But what we actually want to do here is we actually want to make sure that we align the actual whole blit to whatever the nearest boundary is, right? And if we align the whole blit to a boundary, what that's unfortunately going to do is it's going to mean that there might be a mask at the start and the end. Because if we are always working on aligned 4 pixel wide options, then that means that the startup and the end might both be clipped, right? So if there's no way getting around it, that's fine. Let's go ahead and work it out. So I'm going to take a look here. I'm going to say, all right, we've got this fill rect. Let's see here. I got to page this code into my own little memory cache. So what I want to look at here is I want to say, well, if we don't really care about the fill width so much. What we care about actually is the min x, right? We need to get that min x aligned, and I guess we need to get the max x aligned as well. And so the first thing that we probably want to check is the min x aligned, right? And so I'm going to start with that. So I'm going to say, all right, if the fill rect min x is not aligned, we'll move it back, okay? So we'll say if the fill rect min x is not aligned, we got to move it back. And I guess we'll sort of say we've got our startup clip mask and our I guess our left clip mask and our right clip mask might be the right thing, because there's one at the end, one at the beginning, one at the end. Or I could call them beginning start clip mask and end clip mask. I don't know. I'm not sure what to call them there, but anyway, we'll got these 2 clip masks. We'll assume that there's no clipping. We'll then say, all right, if the fill rect min x is actually something that's going to be unaligned, we'll go ahead and align it. So we'll say that the min x is going to knock out whatever those bits are, right? So the min x gets knocked down. And I guess we could say new min x maybe equals that, and then say fill rect min x equals new min x, like so. And we need to go ahead and make our masks here. And I feel like we might as well just do that actually in this is actually, you know what? We don't even need to do that. This is going to be a lot simpler than that. What we can really just do here is say startup clip mask equals, clip masks. And we'll just go ahead and make a little table of them, since there's only going to be a few, right? We'll just say that whatever it is and 3, look that up, and that's the clip mask, right? And then go ahead and make sure that it is actually aligned. Okay? So that's pretty straightforward. Then what we have to do is say, all right, if the max x is also not aligned, then that one has to be aligned as well. And that's going to be the exact same thing, only unfortunately this time it's got to round up, not down, right? And so we need to, we'll have to check out the clip mask thing there. It's actually just, I think it's just we could actually just subtract the value from it, but we'll take a look at that in a second. Anyway, so the fill rect max x here is going to be, done the exact same way to knock out those bits, but then we can just add 4 to it to basically round it up instead of down, if that makes sense. So that seems pretty straightforward there. So once we have those aligned, I don't know if fill width are either of these things used ever again. No. So we should be able to actually kind of blow these away, I think. I don't think anything has to happen there. So if we change all the fill rect up there, then really all we need to do is make our clip masks here. So this will be the M128i clip masks. We need to set those. So we need to say we've got each of these, right? Something like this. And those will be correct for startup clip masks, right? So this is essentially taking what's set to all ones, right? Oops, I gotta put end clip mask there. This one's set to all ones, and then we go ahead and we shift it so that we end up with ones that are properly done for the startup. So this goes ahead and masks out the first, this one goes ahead and masks out the first pixel, this one masks out the second pixel, this masks out the third pixel, right? Now we want to do the exact same thing for the, I guess I should do it this way. We want to do the exact same thing for the startup and the shutdown clip masks. So there's start clip masks, there's end clip masks, and like I said, we could probably do this a little bit cleverer, but I don't want to get clever just yet. So we'll do this the straightforward way. And all this is going to be is the exact opposite, right? This is just going to be shifts in the opposite direction. So instead of masking out the first pixels, this masks out the end pixels. So however unaligned that max x is there, we're going to do the opposite thing. Wait, I got to think about that. Is that actually correct? So, well, let's just do it on the blackboard instead of thinking. It's always better to do the drawing. So at the end, what's going to happen here is that if they're right on the 0 boundary, then we don't have a problem. It's aligned, right? But let's say that it was here, so that it actually has to write one of these guys. Then what we want to do is we want to have, in our processor order, right, like so, we want to have F's down here and zeros up here, right? So what we wanted to do is we want to have sort of a shift. We want to shift this way. We want to shift right, right? And we want to shift right by 3, right? So I think it actually looks something more like that, right? 3, 2, 1, like so. So I think we want to do something actually more like that, right? And technically we could even, if we want to here, just do these. These don't actually have to be predicated. I don't know if we want them predicated or not, but we don't actually have to have them predicated, right? So anyway, we've got start clip masks and end clip masks. I think those are set right now. So this one would be, shift out 3 of the pixels. This one would only shift out the first 2. This one would only shift out the first 1. And I think that's what we actually want, right? Because as that gets up higher in terms of where it is on alignment, that's what we want to do. And so we have a start clip mask and an end clip mask. The only problem is now we don't actually know when to use the end clip mask, right? Because the routine already handles that startup here where it does it resets the clip mask to be -1. But what we have to do now is, and this is why I say it's a little ugly, is unless I'm missing some clever thing, and this is why I didn't really want to do it in the first place, we actually have to put in some predication here to actually set the clip mask, right? We have to do something where we're going to check to see what the status is in terms of xi, right? Because you can kind of see it stepping up here. Now, I don't actually know. xi is never used anywhere. So what I'd like to do here is potentially make this a little bit friendlier for the test, right? So we can maybe loop over something other than that. So we'll do that in a second. But for right now, what I'll do is just say, okay, if whatever xi is going to be next, right? So I'm going to, if xi plus 4, that's the iteration we're about to do, right? if whatever we do next plus 4 would be outside the bounds, then that's going to be the last one. So I want to actually go ahead and set the clip mask to the end clip mask on that final run, right? If that makes sense. So that's what I want to start out by doing, right? Oops, start clip mask, end clip mask, there we go. And start clip mask, there we go. So I want to fix that up a little bit potentially, but I just want to see if we're getting a little closer there. Ooh, that's a little ugly. A little bit ugly. That is not quite correct. I think we all have to agree that that does not look fabulous. I think we're all on the same page there. But you know, it's getting there. Oh, whoops! I've got the sense of this reversed. If it's under max X, it's not on the last one. So that's okay. That's problem number 1. Sorry about that. Okay. So actually, now we look a little more correct, right? That looks like a more correct blit, and we are also not crashing, which is a nice aspect of it. So what I want to do now is see if we're always aligned. So I'm going to take out these U's, the store U and the load U. I want to go ahead and make sure we're always loading and storing actually aligned, right? And so we shouldn't, those will crash if they will like actually fault if we're not aligned. So I just want to make sure that we're not getting that crash, and there we're not getting that crash. Okay. So let's step it up another notch, make sure everything's kosher here. I'm going to set us to O2 and see how we're doing. In O2 we're doing pretty good here. That's looking okay. So that's not too bad, right? That's all good. And I'll go ahead and also see what happens if we turn on threading. Tiled render group. Here we go. So there we go. So it's looking pretty good. We don't have those nasty tiles anymore, so that's all nice. And so I think that's pretty reasonable. Now the platform code has to still be guaranteeing us that it's doing that it's allocating the memory aligned. And I want to go just double check to make sure that it is in fact doing that and that we're not getting that by accident, if that makes sense. Because again, this assertion here, we need to make sure that these are all actually assumptions that are not going to be totally invalid, right? So let's take a look. If I go in here to where we allocate that, right? You can see us virtual allocating this here. And so in here we do the Win32 resize div section. That's where we do the virtual alloc with our bitmap memory size. You can see the bitmap memory size here is not actually doing anything in particular to make sure that the sizes are rounded properly, but virtual alloc will always return us memory that starts on a page boundary, which by definition will be aligned to actually, I think, 4K, not just 16 bytes. So it'll be way over aligned for that. But the problem is the pitch here, we don't actually have any guarantee that we're actually going to be aligned to 4 pixel boundaries. So what I want to do is make sure that we're aligned to 4 pixel boundaries at least when we do this. So what I want to do is change the way that we're making this happen a little bit here. I want to go ahead and bring the pitch computation up above here. I want to say that the pitch computation is going to be the width times bytes per pixel, and then I'm going to allocate based on multiplying the pitch times the height. And what I want to do there is I want to go ahead and round this value so that this value will be rounded to an even multiple of 4, right? So I want to say, or to 16 bytes, basically, right? So I want to do something, I'm just going to call it align 16, right? And I want align 16 to align things properly. Now, I don't know if we've ever actually put in any kind of alignment code into anything here. I don't think we have, but I'd like to kind of introduce that. So what I want to do is introduce a thing, align 16, which takes some kind of a value, doesn't matter what the value is, and then does exactly what's happening in these things here, right? It's something that's going to produce the desired rounding, right? So what I'm going to do there is I'm going to say I want to take the value, whatever that value is. I want to add 15 to it, right? And then I want to mask out whatever the part of it is that would have been unaligned, right? So this will round it up, right? This will round it up to the nearest value that is a multiple of 16. So that way we can guarantee that that pitch is always going to actually be always going to be valid for the assumptions that we have in the renderer, which again, it was already happening because of the width that we happen to choose, but I just wanted to make sure that that would always be the case, because now our renderer literally cannot accept anything other than that, so we wanted to make sure that that's fine, and now that is fine. So I think we're good now on rendering. Everything looks fine. Here we are at 1920 by 1080, and everything's fine, so that's all good. We still haven't actually done anything with our sorting or any of that stuff yet, but we're in good shape here, I think. That's all pretty reasonable. How much time we got left here? We got 2 minutes left. So we did that. That's all good. We'll come back here. We can remove this now. We've got the assertion in there, so that'll fire in the case where we have a problem. I can also, I suppose, based on looking at how this was with O2D, our game, even at 1920 by 1080, is totally fine to use right now, even in debug builds, because if we turn multi-threading on, we just get a pretty big boost from it. So that's nice, obviously. But at this point, I also want to go ahead and maybe just play with it a little bit to make sure nothing breaks. I know what I can do in the last 2 minutes, actually. This will be better. So Martin's pointed out something that we forgot to do. I don't know if you guys noticed it. I'll show you what the problem is, but for some reason, and I don't know why, I just wasn't thinking, I put these global pointer assignments inside memory as initialized, but the problem there is that doesn't actually help us during reload, right? So if we're using our hot reloading function, you know, we're doing all this sort of stuff, and we go ahead and we do a hot reload, we'll crash, and we'll crash because we do not actually have the valid pointers anymore, because our global memory, our global variables, our statics, all get wiped whenever our DLL gets reloaded. So the more proper thing to do, and what I should have been doing the entire time, is I should always be setting up those pointers right at the beginning, right? You should always copy them in, because in case we got reloaded, we want to make sure that that's the case, right? And so now we can just verify that we don't actually crash. So that was something that I should have done. All right. So now we're actually rendering very nicely. Everything is kosher. Everything looks nice and smooth and pretty. So that's all good. We should probably take care of our debug rectangles at some point, because they're not subpixel correct. Maybe we never really care about that. But so yeah, so that's good for today. And I think that now that we're doing aligned with and we've got the masking in there, we're in good shape. I worry when we go back to return to optimizing that function. I'm a little nervous about having to have that extra branch in there, but I'm hoping that maybe that doesn't work out to be that big of a deal, because hey, the x64 is actually really good at branching, so we may be fine. So that should be good. All right, so we'll leave that. We'll go to the Q&A. I don't know that there'll be a whole lot of Q&A, because really all we had to do was do that alignment stuff. But if you have questions about alignment, now would be the time to ask them. Okay. The bitmap memory size calculation squares bytes per pixel. Ah, did I not remove one of the bytes per pixels? Ah, thank you. Yeah, so when I moved out the pitch, I forgot to delete this bytes per pixel, which doesn't need to be there anymore. So thanks for catching that. That's good. Yeah. Because you see, we pulled out the bytes per pixel into here, so we didn't actually need to keep it inside. Wouldn't actually do anything, but it just wastes memory, right? Because we know we're not going to use that memory. So yeah. Can you test if weird resolutions are actually working? Yes, and that was what I was kind of saying before going to the Q&A I wanted to kind of do. I want to test two things. First thing I want to do is test like weird stuff with this, right? Because I don't actually, we could have some bugs in the math where like it doesn't work properly if we set weird tile sizes, right? So I want to just make sure that, we can pick whatever we want there and it doesn't go down in giant flames. So there's you can see a bug there that we have, which I'm not sure whose fault it is, but you can see that actually in the renderer for the tile chunks, they appear to be off slightly. So that's something we should probably track down. So we're working fine, but we do have some kind of a clipping bug, right? I don't know. That may not come out on stream, but there's a very little, there's a hairline part where it did not fill. So it's like it was over clipping or something to that effect. Oh, well, you know what? That's just because this is not rounding, though. That's all that actually is. So what we have to do here is we have to make sure that we need to be able to round up the tile width, I guess, like I was sort of saying. If the tile count here doesn't divide evenly into it, we're rounding up the tile width so that it fits in that it always is a power of 4. But we need to do something to make sure that we always fill the correct number. What we probably should do is just adjust the last one. Maybe we should do something more like this. I don't know, what do you guys think of this? If we just say, if this happens to be the last one, right? If this is the last tile in either direction, we just make sure that it actually, that it actually goes all the way to the end, right? So that may be the better solution. So that's going there. Okay. So that seems good. So 9 is probably not a good number. I'll leave it at 4 here for now, although we may actually want it to be smaller than that. We'll see. I'm not actually sure what the optimal number is, but we'll do some timings. So let me also check while we're at it the actual overall resolution. So if we want to run in some totally weird thing besides 1920 by 1080, right? If we're trying to run in some really weird mode, I will go ahead and just introduce some graphics number like 1371, let's say, by 913, or better yet, well, you know what? Let's get some primes in here that aren't divisible by anything. Prime list of prime numbers. Let's take a look at the prime numbers. So let's do a prime number. How about I'm feeling good about maybe something like 1277 or 1279. Nice and prime. Nothing divides into it evenly, so that's good. And maybe we'll go out and grab. How do you feel about maybe 719? So it's pretty close to 720p mode there, but it's totally prime, so nothing divides evenly into it. And let's make sure. So there you go. Awesome. So you can see we definitely have a bug somewhere where we're not incrementing one of the values properly. So that's a good thing to test. We're running just fine, but our pitch is off. So we need to go figure out why our pitch is off. Now what's weird is this almost looks like it's maybe just the blit in Win32 that's off. So I want to go double check that blit first. I don't actually know what that does. So stretch DI bits, buffer info. So the pitch is not actually being used here. So I actually suspect that it's actually just this code that's wrong. That's my suspicion. So I'm going to take a look at stretch di bits and see if it accepts a pitch okay. In like the bitmap info, I'm assuming, is where that would go, because you can see there's no mention of pitch anywhere in here. So we've got to go make sure that's actually going to be right. So in the bitmap info header, this may be a non-starter, unfortunately, right? There is no pitch, it looks like. So we may not be allowed to use stretch. So honestly, I think that's probably all that is the thing we're using to copy it to the screen can't handle an arbitrary resolution. So I think we actually are handling it, but they are not handling it. So yeah, that's unfortunate to say the least. But that just looks like how it goes. So yeah, we can't really do much with that, I'm afraid. What we can do is we did verify that it looks like it renders properly in our code anyway, but stretch di bits is not going to accept that. I don't know, we could probably try to create something else here, but yeah, I mean, copying it to Windows, we just have to do some kind of a copy ourselves there anyway, right? So anyway, I think that's roughly correct. The other thing we could do is we could change the back buffer inside the actual renderer to be different. So for example, we could do something where we set it to 1920 by 1080, so it's always running properly through Windows, and it doesn't need to know about our pitch and what's happening there. But then what we could do is inside the renderer itself, when we come in here, we could just fake the size, right, to be different. So for example, in handmade.cpp, where we do the output target stuff, let's go ahead and see where that actually is when I do tiled render. So we've got draw buffer, right? So here with draw buffer, we kind of go ahead and set up this stuff for the buffer. So what I'm thinking is maybe we can just here do a little thing where we hard set it so that even though Windows has the backing store that it's okay with, we still run in a prime mode and see how that goes. So that that looks sort of correct to me. Yeah, I think we're all good there. Looks pretty reasonable. All right. Okay. So yeah, I think I'll leave that in here just so we have a note Casey enable this to test weird buffer sizes in the renderer. And there we go. Will you check for cache aliasing? With this much alignment, hitting cache aliasing is much easier. Unfortunately, I can't check for cache aliasing very quickly right now because we need some ability to go read performance information, which we don't really have at the moment. So eventually we could get there, but yeah, at the moment, no, I can't. And cache associated, yeah, I know what kind of aliasing you're talking about. We'll try to get to that later. That's kind of a very advanced topic, but we can try to get to that later. Maybe we can run some Intel performance gathering library that will allow us to read like L2 cache misses and stuff like that from the chip, and that has some aliasing data in it, if I remember correctly. So you can actually look at those. what about the extra pixel around the edges to deal with bilinear filtering? Will you get rid of that? I don't know if we will ever get rid of that. We will take a look at that maybe, I'm not sure, somewhere possibly this week when we go through and just look at what we're doing regarding pixel centers and stuff. But we may not ever fix that depending on how we choose to do our bitmap stuff. We may end up making it so that what we actually do there is we always pad our bitmaps so that we can fetch a little extra. Looks like that is the end of the questions. Did I not recompile with that if zeroed out? There we go. Yeah. And so one of the things that that I'll do, and I guess maybe we should do this sometime soon. I'll have to update the art pack with full res assets because I asked Yangshin to do all the assets for 4K resolution, and so all these are actually downsampled. I downsampled them because when we started working, we didn't have scaling. And so what I probably will do is we'll go ahead and properly size them now for 1920 by 1080, since obviously that's what we're going to want to run the game in. And so I'll only scale them down by 2x for use. So we'll have to do that eventually. I don't know when we'll do that. Maybe in a couple weeks when we want to start playing around with some of the other stuff. Maybe after we're done with debug output. So yeah. Will you keep the rendering of the two lines on separate hyperthreads? So we haven't actually done that yet, right? And the reason for that is because, and it's something that we have to get to, or at least, I mean, to be honest, maybe what we should do is just not bother anymore with it, because I wasn't expecting the renderer to be so fast as it is already. And so it might not be that useful for us to belabor the point. But as you can see, we're not actually using two hyperthreads yet. We just have a single thread do both. And so the reason that we're doing that currently is because with the job queue, it's actually somewhat difficult for us to make sure that the same core will grab two of the same tile and then use threads interleaved. It's kind of tricky to figure out how to really make that work, right? And so that's like sort of a separate thing. And so since it's so fast, doing the rendering the way that it's doing it, I am wondering whether it's something we just actually don't need to do. And I don't know. I really don't. So yeah, it's tough to say. And it may be something we should just bolt and get rid of the every other line thing entirely, right? That may just be better. And for the person who's asking whether it's going to be a 4K Zelda 1 style game, it's actually not going to be 4K. I just had the art assets done in 4K because I wasn't sure how we needed to scale them exactly. So it'll be 1920 by 1080. Is what it'll actually be. And at some point, maybe several years down the line, when people actually have 4K displays and actually have graphics cards that output to them reliably and stuff, we could ship a very large version of the game that had the 4K assets in it potentially as well. So I don't know what we'll do there, but yeah, I mean, the long and short of it is we should have the capability to run at 4K in terms of art assets at such time when that actually makes some sense. But at the moment, the vast majority of people don't have a 4K display, not to mention whether they necessarily have a machine that would run it. So it's not really, that's not part of the goal of this game. All right, looks like we are concluded. All right, so this is good. Today we've got our renderer in a place where now we could actually use it because it doesn't have weird tile boundaries on it anymore. So that's a good thing. That's all very good. And so what we need to do tomorrow is we need to start taking a look at some other aspects of that code. I want to go through and just tighten up some more things. Maybe take a look at the sort of the render queue, the way things are flowing through it, and just the way that pixel centers and texel centers work in that code. I just want to kind of do a pass now that we've done a bunch of work on it here. I want to do a pass to make sure everything's kind of kosher there and we don't have any weird surprises going on. But that does seem like, hopefully that wouldn't take too long. Just want to do some of that stuff. And maybe we'll try to, I don't know, people always seem extremely upset about sorting. So maybe we could also kind of roll that in there. I don't know. But they hate it when he comes here and he's not behind the tree. Everyone just can't deal with it. I don't really know why, but they can't handle it. So we could do that potentially as well. So anyway, just want to start doing some render cleanup passes, get us down to the point where we're in a place where we're comfortable. We've got the threading working. We've got an optimized version of one of the blitz. Well, it's actually a texture mapper at this point. We got an optimized texture mapper. Then we'll have sort of clean up the render queue, and we can actually take a look at okay, here's the whole renderer. Here's how the performance looks like right now. What's the memory throughput in total that we actually are getting, and how close is that to the maximum, so that we have some idea of what our performance is. So we'll go ahead and do that tomorrow. And again, same time, same place, 5 p.m. Pacific Daylight Time here on Twitch. So hopefully that will be something you will come and join us for. I'm going to go ahead and shut things down here. See, get rid of bitmap info header. All right. Thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always go to handmadehero.org and pre-order the game. It comes with all the source code so that you can play around with it at home. We also have a forum site where you can ask questions and view the annotated episode guide, get ports to Mac and Linux, all kinds of good stuff. We have a Patreon page if you want to support the video series. You can subscribe to that. We also have a tweet bot, which tweets the schedule at you, and we have a little live button, which gives you a countdown till the next live stream. So check all that out. It's all pretty useful. And in the meantime, until tomorrow at 5 p.m., when I hope to see everyone back here, have a good time coding, and I will see you all on the internets. Take it easy, everyone.